Let's take a look at some weighted graphs and see if we can't come up with a minimum spanning tree for each one of these weighted graphs. Remember, there are two ways of doing it. There's Prim's algorithm, which says we pick a node, and then from that node we figure out what the lowest weighted edge coming out of it is. We add that to our tree along with the node that it was connected to. Now, from the nodes that you have in your tree, you figure out what the minimum weighted edge is out of that group, and you pick that one, add that to your tree, as long as it does not create a cycle, because as soon as you create a cycle, you no longer have a tree. Let's go ahead and use Kruskal's algorithm, which Kruskal's algorithm for this number 35, Kruskal's algorithm says we are going to create the minimum spanning tree by simply looking at the edges, adding an edge along with the associated nodes, and keep adding the lowest edge that is available without creating a cycle. So if we look at this diagram, this wheel here that has got connections like a spoke, what you're looking at is, let's see, we have 2. 2 is the lowest level and the lowest weighted edge. So we're going to go ahead and add 2, which adds 2 nodes. Now, there are no more 2s, there's no 1, but there are 3 3s. And so let's pick from one of the 3s to add to this tree. None of them create a cycle, so I can add any one of them. I don't know, let's just add this diagonal bar right here. So I've got a 3 and a 2. Now, the nodes are not connected. We don't have a tree yet. Or spanning tree, but we've got 2 edges with no cycles. And by the way, how many edges are we looking for? Well, if you count up the nodes here, we have 1, 2, 3, 4, 5, 6 nodes, and that means that we are going to have exactly 5, or 1 less edge than we have nodes. So what do we add next? We still have a couple of 3s we can add, neither of which adds a cycle, so just pick one. And so we add 3. And that guy added another node to it, but we didn't create a cycle, so it's good. We'll go ahead and keep that. And that brings us up to 3 edges. Remember, we're looking for 5. What's next? Well, we can add this 3 here and without creating a cycle, so that 3 can stay. And it looks like we've added all the 3s. Now we have to move to the next one, and that's 4. Well, there are 2 4s here. Neither one adds a cycle, but it turns out that both of them, either one, will complete our spanning tree. So I don't know, let's just grab this guy right here. Now, we've got a spanning tree. We've got 1, 2, 3, 4, 5 edges for 6 nodes. Now we should have the ability to sum up our total weight, the sum of all edges for this minimum spanning tree. And what we've got is 3 plus 3 plus 3 plus 4 plus 2. All right, I think that's all of them. 3, 3, 3, 4, and 2. And that's all the weights for all of our edges. And so we got 3 plus 3 plus 3, that's 9, plus 4 is 13, plus 2, that is 15. So our answer to this problem is 15. Now, if we move down to problem number 36, we used Kruskal's algorithm for the first one. Let's use Prim's algorithm for this next problem, number 36. And I don't know, you just pick a node, any node. All of them are going to have to be included in our tree, right? So let's go ahead and include B. And notice that I've got the vertices over here in exactly the same pattern that I have them in the connected graph. In the weighted graph, all you need to do is fill in the branches or the edges that you've selected on this set of points on the right-hand side. So from B, we've got 4, 5, and 6. Those are all of the edges coming out of B. Well, the one that's minimum is this 4. So that's the one we are going to first include in our tree. So we go ahead and we add the 4 to connect B and A. And now we have B and A along with 4 selected. Now, all the edges coming out of B and A, you have the 3, the 5, and the 6. Does it matter which 3 we pick? No, it doesn't. It's going to still result in a minimum spanning tree. It might result in a different set of connections, but it'll always result in the minimum spanning tree. So let's pick one of the 3s. I don't know, how about the one on the top? We'll pick this branch over here that goes to E. And so we add it to our graph over here, and we have 3. All right, now we have, and remember, let's count our nodes. We've got 1, 2, 3, 4, 5 nodes, or 5 vertices. So that means we're going to have 4 edges. We have 2 more edges to go. Now, from the 3 points that we've got, what edges are connected? Well, we've got this 6, this 5, this 3, and this 3, and then this 4. What's the minimum? Well, it turns out one of the 3s is the minimum, right? So we need to pick one of the 3s that is connecting us to D. Does it matter which one? No, it doesn't. So I don't know. Let's just pick this guy right here to grab D. So we're going to grab that guy. There'll be a 3. Now we can't use 5 anymore because the 5 is going to make a cycle. 3, that other 3 is going to make a cycle, so we can't pick either one of those. All we've got at our disposal now is the 6, which will connect us to C, the 2 that will connect us to C, and the 4 that will connect us to C. What's the smallest one? It's the 2. So we can go ahead and grab the 2, and that will give us our minimum spanning tree to connect all 5 of these points. Now, something that we could do is, instead of connecting D the way we had connected D, is we can connect it to A through that 3 edge that connects to A to D, and that would have just simply changed our graph, but it wouldn't have changed the total weight. The total weight right now is 12. Well, if we replaced that 3 that connected A to D, this is still a minimum spanning tree. Either one of these answers would have been correct. We still have a weight of 12. Now let's take a look at problem number 37. Problem number 37 says both Kruskal's and Prim's algorithm, true or false, will result in the same final sum of edge weights for the same weighted graph. Now remember, I'm not saying that we're going to end up with the same minimum spanning tree. I'm saying we're going to end up with the same weight, and that in fact is true.